A runway excursion is not as fun as it sounds. It's like off-roading, which is fun, but in an airplane, not so fun anymore. In a best-case scenario, it looks something like this. And in the worst-case scenario, something like this. Thankfully though, there is a remedy to this problem. This device can help prevent some of those dangerous accidents. It looks like a French press, but trust me, it's not. And this is a special building where inside, pavement ages. Quickly, for real, there are in fact a series of procedures that you may have never heard of because they happen behind the scenes, without which there would be a lot more off-roading in our airports. That said, accidents can still happen. But what these special rocks are, what they're actually made of, and how they can bring an aircraft that's moving at 80 miles per hour to a quick and safe stop is not what you think. On December 6, 2018, a Southwest Airlines Boeing 737 overran a runway during landing at Bob Hope Airport in Burbank, California. Apparently, the pilot had overshot the ideal touch point. Luckily, the airplane came to a stop, and that was thanks to the arrestor bed that had been installed at the end of the runway. More on that later. But aside from human error, runway excursions can also be impacted by poor weather conditions and mechanical issues. Pilots receive extensive training on runway safety, including how to handle emergencies, how to avoid overrunning the runway, and how to make safe landings in various weather conditions. That training is absolutely necessary, but it's not always sufficient because when things get wet, even pilots can lose control. I'm talking about hydroplaning, when the airplane slides on the wet surface of the runway with little to no control. The layer of water that forms between the wheels of a vehicle or airplane and the surface of the road or runway can reduce the friction between the two surfaces, making it difficult for the vehicle or aircraft to maintain control. When still water accumulates on the surface of the runway, the risk of hydroplaning is significantly increased. This is why some runways have grooves, which not only act as channels for water to escape, but they also improve the traction of the aircraft tires on the surface of the runway. Along the same lines, the surface of the runway must provide a minimum amount of skid resistance. To test for this, the US Air Force has the APE team, Air Fuel Pavement Evaluation, and the APE team has some interesting tools. This is a friction measurement machine that can determine the texture depth of the pavement. Think of it as the roughness of the surface, which determines the skid resistance of the runway. The nozzle shoots out specific amounts of water under the wheel to simulate different weather conditions. The test is being repeated here on the grooved part of the runway. Another way to measure the friction values is to use a hydro timer. The smoother the surface is, the longer it takes for the water to drain. Over time, as the pavement is exposed to traffic and weathering, the texture depth can decrease. To rehabilitate the pavement, a skid abrader can be used. Skid abraders essentially rough up the surface, which is visible if you compare the pavement in the front versus behind the truck. But still, with all these safety precautions, airplanes can overshoot the runway, so a backup plan is needed. It is possible to bring any airplane to a quick stop once. That's why we earlier said a quick and safe stop. This is probably more like it, but why is this airplane tearing up the runway? The length and width of runways are important factors in preventing runway excursions. In the 1960s, the introduction of faster jet, like the Boeing 707, required longer runways. So the FAA proposed increasing minimum runway, but there was a strong industry pushback. Proximity to populated areas, bodies of water, and other natural barriers could prevent some airports from creating this buffer zone, such as LaGuardia Airport in Queens, New York. To enhance runway safety in such airports, 1990s, the FAA began conducting research on new technologies that could bring aircraft to a rapid stop safely in less than 1,000 feet in the event runway overrun. The answer was Engineered Materials Arresting System, or EMAS, a high-energy absorbing material that could be installed beyond the end of the runways. Sometimes referred to as an arrestor bed, EMAS is made up of lightweight and crushable materials that are designed to collapse under the weight of an aircraft, usually above 12 tons. As the landing gear sinks into and rolls through the material, the aircraft gradually decelerates. But what is EMAS exactly made up of that can stop an aircraft moving at a speed of 70 knots? These pebbles are what is at the core of the EMAS. They may look like rocks, but they're quite the opposite, as they're light and are easily crushed, more like styrofoam. The pebbles are typically made up of high-strength materials such as expanded polystyrene or expanded polypropylene, designed to compress and absorb the energy of the aircraft as it comes to a stop, which helps prevent injuries and damage to the aircraft. October 27, 2016, when a Boeing 737 with 37 people on board, including then Vice Presidential candidate Mike Pence, overran the runway while landing at LaGuardia. Thanks to the EMAS, the airplane came to a stop with no casualties or serious damages. One way to install EMAS is using prefabricated blocks. Prefabricated blocks can be simply unloaded and placed side by side and are ideal for smaller projects. But for bigger implementations, the construction is done on site. The area is first partitioned into segments to house the pebbles. The pebbles are then poured in and leveled off. They are then packed in preparation to add the top layer, which is a layer of concrete. The coating is prepared and applied once the concrete sets. This is done in order to protect the top layer against the elements. EMAS installation is good for 20 years. EMAS doesn't require much maintenance once installed. Any damages can be patched as needed. Even if an airplane overruns the runway and engages with the EMAS, only the damaged parts need to be cut out and replaced. EMAS has been installed in over 100 runways in US airports. Of March of 2022, 18 overrunning aircraft have been safely stopped using EMAS because when it comes to aviation safety, the durability of the runways is just as important, which is why inside this building, pavement ages quite quickly. These are two test vehicles attached to two radial arms that are 30 feet long each. Their job is to accelerate pavement testing. The vehicles move at just over 31 miles per hour and can do 50,000 cycles per 24 hours. Water can also be applied in a controlled manner as required to create different testing environments. Accelerated pavement testing can provide expedited feedback on new designs and materials for the roads. And remember the APE team. They don't just evaluate the friction measurements on the runway. Every drop from this heavyweight deflect meter simulates a fully loaded C-17 moving across the runway. The trailer-mounted device operates by dropping a weight that hits the pavement with up to 55,000 pounds of force and measures the resulting pavement deflections to determine the pavement layer stiffness. And this machine takes destructive samples of the runway by cutting deep into the underlying materials. A 6-inch core is cut out and dug up, which is later analyzed to ensure it meets the requirements. And that's a good reason why you wouldn't want to bury a body under a military runway. Ensuring the quality and safety of runways is a critical aspect of aviation. Infrastructure, which requires ongoing investment, maintenance, and attention to detail, to ensure safe and efficient air travel. And that's why, while we're asleep, these two are hard at work. Not those guys. These guys,